Hello students, welcome to physics class on vector analysis unit 1 under paper 1 mechanics in your semester 1. This is N. Chandana, assistant professor of physics from Government Degree College, Khairabad, Hyderabad. Let us have a quick recap on our previous 2 classes on vector analysis, which is your first unit of mechanics. We have learned what are scalar and vector quantities and what are the addition of vectors and then properties of addition of vectors. Then we have learned the resolution of vectors, then scalar product of two vectors, vector product, that is dot product and cross product of two vectors, and then triple product and of scalar and vector. And then we have been to some problems regarding all these types of concepts we have learned in the previous 2 classes. Okay, next let us go further quickly to the next topic, that is scalar and vector fields. Okay, so let me share whiteboard. Now let us go for scalar and vector fields. So what is a scalar field and vector field? Let me write here. What is a scalar field and vector field? Field, yeah, you're hearing the correct. Field, what are these? We know that every physical quantity can be expressed as a continuous function of the position of a point in the region of space. Okay, like if I have this space, now every physical quantity can be expressed as a continuous function of the position of a point in the region of space. Now it can be expressed as a continuous function in this region of space, any physical quantity if you consider. For example, let us take a small example. When a rod is heated, you take a rod, okay, iron rod. If a rod is heated at this end, okay, the rod is heated at this end, then you are able to observe the variation of temperature along the length of the rod. So here you can observe the heat, that means the change in temperature, the increase in temperature after some time, right? Because there will be variation in temperature along this region of space, region of rod, along the length of the rod. Then this physical quantity temperature at any point here or here, here or here or here can be expressed as T of x comma y comma z. Okay, such a function, this function is termed as a point function or point function or function of position, point function or function of position. Okay, see, this is a small example, and this temperature is always a scalar. Hence, the field associated or linked up with this scalar function is said to be scalar field. Is said to be scalar field. I hope you understood now. So the field associated with the scalar function with respect to the region of space, in which the point is confined, that field is said to be scalar field here. Okay. Now, for a scalar field, like a scalar physical quantity is assigned to each point in a space, then we can say that it's a scalar field in the region of space. Now, in general, the scalar field is expressed as phi of x comma y comma z, or sometimes psi of x comma y comma z. So by these two parameters, any scalar field can be designated. Okay, then comes example. For example of a scalar field. Let me give you example of scalar field. Scalar field. So examples. We have scalar potential. That is electric potential. The potential is a scalar, right? Now, electric potential due to a single positive charge Q depends on the position of the point from the charge, right? At some position it may be x naught, y naught, z naught. At some other position it may be v1, x1, y1, z1. So these are scalar point functions at positions x0, y0, z0 and at point x1, y1 and z1. Now the region in which the scalar potential we can calculate, that region is said to be scalar field or this scalar potential field. Okay, this scalar potential field. This is not a vector field because it is a scalar. Electric potential is a scalar. Okay, density. The density at any point inside a body occupying a given region is also called as a scalar field. Also called as a scalar because density is a scalar. The field associated with density function is also a scalar field. Now let us go for scalar field, and we have already discussed examples of scalar field. Let us go for vector field here. Come on, let us go for vector field. Examples of vector field are more popular, you know, electric field and magnetic field. So these are main examples of vector field which you have learned in your intermediate. So when a vector physical quantity is expressed from point to point in the region of space by a continuous vector function a, x, y, z, then the region is said to be a vector field. So when a vector physical quantity is expressed from point to point by term point to point x, y, z in a region of space by continuous vector function a, then this a bar, then the vector, this vector function in the region of space, this region of space is said to be vector field. This is called vector field. Okay, we consider this electric and magnetic field are the examples, and also we can consider the velocity of the body of a rotating body. You can take. Okay, I'm just giving you a normal example. Velocity of a rotating body about an axis, about an axis. It can be treated as a vector field. So the velocity of the body is different at different points. That is, the velocity is a function of position of the point. Hence, the velocity can be expressed as a vector field. So the body is rotating with respect to this point, this axis, this axis. This is the center, outward direction. So now this body head here there is one velocity. Here there is one more velocity. Here there is this velocity. Here there will be tangential direction. The velocity will be there. So here there will be one velocity, here there will be one velocity. In this way, we can give the directions of velocities. So the velocity is different in the different directions based on the positions. So this can be treated as a vector field. Now we will go for the other concept, polar and axial vectors. Polar and axial vectors. You have to learn this. Polar and axial vectors. What all these? Polar and axial vectors. What all this? First polar we will see. Polar, other name of polar is radial vector or real vector. So they can be called as polar or radial or real. So what are these vectors? They are some physical vector quantities which have their own inherent directions. So for example, I will give you for force. Okay, so you take it as a force. If my physical quantity is force, this is a vector. So which have their own inherent directions. It has its own inherent direction. It has its own direction. Such type of vectors are said to be polar vectors or radial vector or real vectors. This is a real time vector. We can observe them. We can measure them directly. And what about axial vectors? For axial vectors, we have the other name called as pseudo vectors. Called as pseudo vectors. They are not real. You understand? Which have no inherent directions of their own. They don't have no inherent directions. Okay, but we assign them the direction, either left hand coordinate system or right hand coordinate system. Okay, and depend on the convention followed by us. Like for example, angular velocity or angular momentum or torque, angular velocity, angular momentum. All these comes under what? All these comes under pseudo vectors. While force, linear velocity, momentum, linear momentum, displacement, all these comes under polar or radial or real vectors. Okay. So these are the main differences between polar and axial vectors. Now let us go for a quick thing on vector differentiation. Now till now we have understood what all the things we have learned, like vector product, scalar product, and then we have come to this pseudo vector and polar vectors now. Then let us go for vector differentiation. Okay. Now I'll clear this. Let's go for vector differentiation. Okay. Now let us take a position vector r bar, that is xi cap plus yj cap plus zk cap. What is this position vector? Which gives the position of a particle at a particular time, at a particular point. This is r bar, the position vector. If I have my system, my origin is here, this is my x-axis, this is my y-axis, and now I have a particle here. So the distance from origin to this one is r bar. The coordinates of that point is x and y. This is a two-dimensional plane I'm drawing. If you take z bar also, the direction also, we have x, y, z here somewhere in the air, not in the xy plane here. This is somewhere in the air in between this three-dimensional system. Then what is the position of this particle? This can be determined. What is that called? Position vector. Position vector. Position vector. The particle's position in the space, three-dimensional space. It is given by xi cap plus yj cap plus zk cap. Now I just want to calculate the velocity. Okay. Now velocity of the particle. Then how do I calculate? Velocity is equal to rate of change of displacement. You all know that. So dr by dt, that is given by dx by dt into I cap plus dy by dt into j cap plus dz by dt into k cap. So this is nothing but the velocity. Okay, so I can write dx by dt as vx. So vx I cap plus vyj cap plus vz k cap. This is nothing but the velocity. These are the velocity components along x direction, y direction and z direction. That's resolution of velocity vector along x, y and z directions in three-dimensional plane. Similarly, I can calculate acceleration. What is acceleration? Rate of change of velocity, that is dv by dt, that is dvx by dt I cap plus dvy by dt j cap plus dvz by dt k cap. Right? So what is vx and vy, dvx by dy, dvx by dz and dvx by dvz by dt? What are those called? What are those called? Ma? Acceleration components along x, y and z direction. So I have equal to ax I cap plus ay j cap plus az k cap. These are the components of the acceleration along x, y and z directions. Okay. Now let us know some of the things, some vector differential operator we have to learn now. Now what is that called? Del bar. Let us learn one vector differential operator. Del bar. What is this? Del. It is known as del. This is delta. This is for change in any property. We'll write it as delta x, delta y in this way. This is delta, while this is called as del. Operator del. This is a vector differential operator. This is a vector differential operator. This vector differential operator del. So del bar is equal to I cap into dou by dou x plus j cap into dou by dou y plus k cap into dou by dou z. So this is the vector differential operator del. Okay. Del is equal to I cap dou by dou x plus j cap dou by dou y plus k cap dou by dou z. This is the vector differential operator del. You have to remember this. Then we have del square. That is del dot del. What is the dot product between any two vectors? It is a scalar, right? So we can write it as del square. That is I dou by dou x plus j dou by dou y plus k dou by dou z dot I dou by dou x plus j dou by dou y plus k dou by dou z. That is equal to, since we know that I dot I is 1, j dot j is 1, k dot k is 1, and rest of all the things get 0 because I and j are perpendicular vectors, j and k are perpendicular vectors, and k and I are perpendicular vectors. Hence we get dou square by dou x square into I dot I 1 plus dou square by dou y square into j dot j 1 plus dou square by dou z square into k dot k 1. That means del square is dou square by dou x square plus dou square by dou y square plus dou square by dou z square. This is del square. This is the Laplacian operator del square. Okay. This is a Laplacian operator. Okay. Laplacian operator. Laplacian operator. Next, let us go for next concept. So far we have learned scalar field, vector field, pseudo vectors, and axial and polar vectors, and then we have come for vector differentiation. In that we have learned del operator and Laplacian operator. Let us go for gradient of scalar field. You have to learn this first concept I'm going to teach regarding fields. Gradient of let us understand, that is gradient of scalar field. Okay. Gradient is only for scalar field. You have to remember that. First of all, what is gradient? See, we have learned in your intermediate or somewhere, we know what is pressure gradient. We have seen change of pressure with respect to altitude. We have learned there. What is change of pressure? dP by dx in x direction. If it is along y, dP by dy, where P is pressure, dP by dz. Gradient means the change in with respect to that coordinate axis along which the physical quantity is getting changed. That is gradient. Here pressure gradient. Okay. Similarly, gradient of scalar field. The main significance of this gradient of scalar field is gradient will form an association between a vector field and a scalar field. How? Because gradient field when a vector field to scalar field, it will associate. How? I'll teach you. It will associate a scalar field to a vector field, or a vector field to a scalar field. How? When I apply, the gradient is denoted by del bar of any scalar function I take, any scalar field. I told you scalar field is denoted by either phi or psi. So if I take my function is phi of x comma y comma z, this is my scalar field. Now that is a scalar function which is representing my field. Now the gradient of phi, that is grad phi, is given by del phi. There is no dot or cross here. There is no product here. That is gradient of phi. That is grad phi is equal to, what is del I dou phi by dou x plus j dou phi by dou y plus k dou phi by dou z. That is nothing but gradient of scalar field. So that's the reason we say that gradient associates scalar field into a vector field. See here, now I have taken a scalar function phi here, and now when applying gradient, the gradient of scalar field has become a vector because I have I cap, j cap and k cap. That's the reason we say that gradient is associated, it brings an association between scalar field and a vector field. Okay. Consider the electric field, the intensity of electric field. Let us see an example. We know that the electric field E bar is equal to minus gradient of V. Where is V? Is scalar potential. That is E bar is equal to minus grad V. If you have the scalar potential, known scalar potential, you can calculate the electric field, because electric field is a vector while electric potential is a scalar. This is an example of scalar field, and this is an example for vector field we have defined already. Okay, so we can associate this electric field to electric potential by using this function is gradient. Okay, that is gradient. Now let us go for some problem on this gradient. Okay, now let me give you one problem. Let us consider the function to be x square minus yx plus z cube. Okay, so this is the function phi I have. Now I am asking you to calculate the gradient of the scalar field at 1, 0, 0. Okay. Now how do you calculate? First I'll go for grad phi or del phi. That is, I get it as I cap dou phi by dou x. What is dou phi by dou x here? You tell me. 2x minus phi. With respect to s only, I have to do the partial differentiation, because here there is no x, it will be 0. 2x minus y plus j cap into, what is dou phi by dou y here? Minus x, because here and here there is no y, it is 0. Plus k cap into, what is dou phi by dou z? 3z square. Now I have to go for at point 1, 0, 0 is the given point. I have to calculate grad phi. Now substitute. For x you have to substitute 1, y 0 and z 0. So what do I get? I cap into 2 minus j cap plus 0. That is 2i minus j cap. See, this is a vector. I have got a vector when I am operating gradient on a scalar function which is given as x square minus yx plus z cube. At a particular point 1, 0, 0, I have got a vector. This is the reason we use gradient to transform our scalar functions into vector functions. We use this function gradient. Okay. Now let us go for next concept, that is divergence. So what is divergence of a vector field? Let us see now what is the divergence of a vector field. For this purpose, let us consider vector field A bar. Consider a vector field A bar. Then the divergence is denoted as del dot A. This is the dot product between del operator and vector A bar, which we have considered in a vector field. The divergence of a vector field at any point is defined as amount of flux per unit volume diverging from that point. Amount of flux per unit volume diverging from that point. Amount of flux coming out of this point, diverging from this point, is said to be the divergence. 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 That means spreading from single point. Okay. Now let me calculate del dot A. You know what is del? I dou by dou x plus j dou by dou y plus k dou by dou z. You have to remember, students, dot axi cap plus ayj cap plus az k cap. Now what is my dot product? Dou ax by dou x plus dou ay by dou y plus dou az by dou z. Now let us see the physical significance of divergence. So that means the major significance or application of divergence. Significance of divergence. Students, in your exam you will be getting these topics: scalar field, vector field, gradient and divergence and their physical significance. You have to learn this. Let us consider that A represents, if A bar represents the velocity of a liquid. Let me consider that A represents the velocity of a liquid. Okay. Then div A or del dot A, that is divergence of A, gives the rate of flow of fluid at that point per unit volume. Gives the rate of flow of fluid at that point per unit volume, that is given by div A. See, if div A is greater than 0, that is positive, then we say that the density decreases. The density decreases at that particular point in the fluid. At that particular point, the density is decreasing, implies this point acts as a source. Okay, acts as a source. If I consider a tap, water tap, now the water will emerge out of this tap's nozzle. So this point of emission, this one, and in the tap, this can be considered as source. Okay. Similarly, when we get div A is less than 0, that is negative, the density is gradually increasing. We can consider that as sink. That means entire water will be coming into our wash basin. You have a sink, you have a hole here. So entire fluid will be reaching here at the particular point. The density here will be increasing rapidly. Hence the divergence is less than 0 of that fluid at that point per unit volume. Okay, but if div A is 0, if I consider that div A is 0, that means how much fluid has entered into this chamber, the entire fluid will be coming outside. There is no variation, there is no increase or decrease in the density of the fluid. Then we say that div A is 0. Okay, when div A is 0, the density of the fluid is constant, then such fluid is called incompressible fluid. Incompressible fluid. So when we say that it's an incompressible fluid, we can directly write down as divergence of A is 0. Okay, divergence of A is 0. Now let us go for some problems. R bar is equal to, we know that R bar equal to Xi cap plus Yj cap plus Z cap. This is the position vector. Now if I ask you to calculate del dot R, that is the divergence of R, what do you get? Dou X by dou X plus dou Y by dou Y plus dou Z by dou Z, because del bar is I dou by dou X plus J dou by dou Y plus K dou by dou Z. So I dot 1, J dot 1, K dot 1. So dou X by dou X plus dou Y by dou Y plus dou Z. Dou X by dou X 1 plus 1 plus 1. It is 3. So divergence of position vector gives you 3. Similarly, you have many problems in this, so you can do later. Now let us go quickly to line integral. Line integral. So what is line integral? The integration of a vector along a curve. Integration of a vector along a curve which is taken by us is called line integral. It's called line integral. Okay, now let me draw a figure for you. See here, if I take a curve in this way, this is some PQ. If I consider a small element here of length dl, okay, of element of length dl, I have a vector a bar from this. Now, if it is making an angle theta here, this is r, if I suppose, then what do I say is the line integral of a vector a. That is the line integral of along the curve PQ, the line integral of a in dl. A along the curve will be equal to integral P2Q dl into a cos theta. So this is the dot product. We say that the component of a along this element dl. Because this is adjacent side, if I imagine some line here in this way, vertical line. Now again we have a 90 degrees. So what we can say is the component of vector a along this dl element will be a cos theta into dl. That gives you the line integral, the integration of vector a bar along the curve PQ. We can obtain in this way. Okay, because I just want this because we have to define the curl of a vector field. We need to know what is line integral. Okay, the integration of a vector along a curve is called line integral. Now we'll go for curl. Curl of a vector field. This is given by del cross A. If my field is A bar, then my vector field is A bar, then the curl of vector field is given by del cross A. Okay. See, we have learned gradient of scalar function, divergence of a vector field, and now this is curl. This is the third one we are learning. There we have applied gradient for a scalar, divergence for a vector. Okay. One second. Then divergence for a vector. Okay. Sorry, divergence for a vector, and now curl for a vector. Now let us suppose what is curl A first of all. We'll just write down now. Curl A. It is I cap, J cap, K cap. You know, dou by dou X, dou by dou Y, and dou by dou Z. Because this is I dou by dou X plus J dou by dou Y plus K dou by dou Z, which is del bar. And what is A? AX, AY, and AZ. Now if you substitute some values here, if a given known vector AX, AY, and AZ components, you can easily calculate the curl of that vector along the vector field here. Okay, curl A is equal to del cross A. In general, what is the meaning of curl? That is, it is rotation. Rotation is called rotation. When we consider a liquid is flowing in this way, in this direction. It's a streamline motion. Now you take a wheel. Now you take a wheel here. It is flowing in this direction and towards right hand side. Now the wheel is not rotating, it's flowing in straight linear path. That means there is no rotation of the wheel, right? Then we say that curl of A is 0. This curl A. But when the wheel starts rotating in this way, so the wheel starts rotating, and it's moving in the forward direction, then we have curl A. Okay, then that field is said to be rotational field. But when the field is irrotational field, with rotation is 0, the wheel will be traveling in forward direction without any rotation. Okay, that is an example for curl. Okay, now let us in brief we'll write down the fields here. A field having no divergence, no curl. Field having no divergence, no curl. What is that field called? Such field steady state. Steady state flow. Okay, rotational motion or incompressible. Similarly, when a field has divergence, it has divergence and no curl. There is no curl. Then such type of uh, fields, examples are gravitational field. Okay, gravitational field inside a mass we can take it, and electric field with a volume distribution of charge we can also consider. This comes under divergence and no curl. Field having curl and no divergence. Field having curl and no divergence again. Such types of fields are magnetic field due to steady current, incompressible fluid. We can say that as incompressible fluid. I told you when del dot A is equal to 0, that is incompressible. Similarly, when del cross A is equal to 0, that is said to be irrotational field. Okay, field having curl and divergence, both are present. Okay, these can be explained by Maxwell's equations within matter. Okay, these can be explained by using Maxwell's equations. Now let us have a quick summary over the things which we have discussed so far. So we have learned scalar and vector fields with examples. A field which is associated with the scalar function, which is a continuous function, so which can be determined by at any point of the scalar space within the space of the scalar function, that is called a scalar field. Similarly, we have vector fields. Vector field we have electric field, gravitational field, and magnetic field. Scalar field we have electric potential, pressure, temperature function. We can have polar and axial vectors. I told you, axial means pseudo vectors, polar means either radial vectors. They are called polar vectors or radial vectors or real vectors. Here they are axial vectors or pseudo vectors. They have inherent directions, but here we don't have any inherent directions. What we give, it will take, like linear angular momentum, torque, etc. Then partial differentiation of vectors. So we have learned what are the operators del bar and how do you calculate the rate of change of displacement here by using this vector components. You calculate. The gradient of a scalar field we have learned, that is grad phi. Gradient will be only for scalar fields, phi or psi. And we associate scalar field with a vector field. The divergence of a vector field and its physical significance we have learned. What is divergence? Del dot A bar, where A bar is a vector field. Now we can understand the significance here. That is whether it is a steady flow or else that it is increasing or decreasing, or it's a incompressible fluid. We can understand these properties by using this divergence of a vector field, by calculating the divergence of a vector field. Now line integral and curl. By understanding the integration of a vector along a curve, we can obtain the line integral, and by using that we can calculate the curl of a vector. That is del cross A. That is curl of A bar. Okay, students. So we had done till line integral curve. Next class we'll learn the three very important theorems which we have in this vector calculus, which are used in drastic applications in our physics. Okay. So thank you, students. Take care.